extension project focused on petrochronology and its geodynamic implications.
We are a group based in Brazil that also has an international network of collaborators. They presently reside in Brazil, Australia, Finland, Germany, Italy, Switzerland, and the US.
Petrochronology involves several areas of the geological knowledge. We seek to disseminate it in a judicious, yet clear and accessible manner.
In our researches, we use macro and microscopic observations, combining fieldwork, detailed petrography, thermodynamic modeling, processes dating, geochemical characterization, and much more.
From the natural record, we seek to characterize and quantify petrological processes in representative samples, generating comprehensive datasets that are interpreted considering the geodynamic processes that govern the Earth system.
We want to share research, from the basic concepts to the state of the art, promoting courses, spreading work results, and providing collaborations between institutions and people.
We understand that open science is vital to take down barriers to knowledge, and we prioritize the collaborative and open nature of our research. We also propose discussions on integrity and responsibility in the scientific environment.
As values, we believe in diversity, representativeness, and access to information. We seek to mirror these values in our initiatives.
On the YouTube channel, we promote the PTt-talk series, which are presentations on methodologies and advances in cutting-edge research with petrochronology.
Our actions also include the organization of lectures, courses, workshops, and meetings open to the community.
On Instagram and Twitter, we share, on Tuesdays, photos of outcrops and rocks in the field, illustrating geodynamic processes.
And, on Thursdays, photos of thin sections with microscopic features with interesting minerals and textures, reflecting different reactions and petrological processes.
So, if you work with petrochronology or are interested in related topics, be sure to follow us and get in touch. We want our community to grow even more. See you!
Hello everyone, welcome to PTt-talk 19. I'm so glad to be here today with our speaker, Renée. Thank you, Renée, for accepting our invitation. We are looking forward to listen to you. Today, Bruno, Maíra, and Guto will be conducting the conversation along with me. At the end, we will provide some time for you to answer some questions you all may have. Now, I will give the floor to Maíra, who will provide more details about our group.
Hello, everyone. So to talk a bit about Petrochronics, as you have seen, we are a research and extension group, and we have several actions that include talks like this one, workshops, and scientific dissemination. And this is our PTt-talk 19. We have like roughly once per month, and we are going now to end the second year. Thank you so much, Renée, to accept our invitation to that. And I would like also to invite anyone that like our content and our actions to become part of the group, so you can contact us. I will be very happy.
Hello, everyone. Thanks for joining us. I'll be just giving a brief introduction about our lecturer. Dr. Renée Tamblyn has obtained both her bachelor and her PhD degrees from the University of Adelaide in Australia, in the latter studying subduction-related metamorphism, including timescale and conditions of metamorphic rocks. while trapped in subducting channels. Currently, she holds a postdoctoral researcher position at the University of Bern in Switzerland, characterizing ultramafic rocks' hydration and dehydration in the Archean, and studying their importance for continental crust formation. Also, she has interest in methods development such as LA-ICP-MS geochronology. To give a brief introduction of the lecture, I'll leave to Brunona.
Well, thanks, Guto. Welcome, Renée. It's our pleasure to have you here with us today. And it's an amazing topic. I'm a big fan, of course, because nothing better than dating metamorphism, right? We need to put some ages on this. And nothing better than doing in-situ laser ablation, because this solution, that's no good. So the talk today is entitled In-situ lutetium happening geochronology of Garnet by laser ablation ICP-MS. And Renée is going to talk to us about the method development that has been done in Adelaide, especially in the last maybe 2 years, and how she applied this for a campaign-style geochronology in metamorphic rocks. I'll leave it to it. Good luck, and I'll be looking forward to hear.
Great. Thank you so much for all the introductions. I feel very honored right now, and thank you so much for the invitation. It's really, really great to be here. Okay, I will share my screen. Eventually. Cool. Okay. Can everyone see that? All right. Whoops. I'll take that as a yes. Or not? Okay.
Now it's okay.
Okay. There's a delay. Cool. All right. Thank you so much. Cool. So thanks again for the introduction. It's really cool to be here. I was really excited to be invited because I followed quite a few of the Petrochronics talk series. And I think it's a really neat way for young researchers to sort of cross boundaries, cross across countries, and be able to interact with each other and talk. And it was developed, of course, because of COVID, but I think it's really excellent that we can keep doing this. It's really great for people in their early career. So thank you, everyone, for running and organizing and inviting. So as everyone said, today we'll be talking about in-situ lutetium hafnium geochronology of Garnet. And of course, I want to point out my co-collaborators here, mostly from the University of Adelaide, and also Adelaide Microscopy, which is our microscope facility in the University of Adelaide. And I also want to say just a special thanks to the University of Bern and the PI of my grant, Jörg Hermann, for allowing me to continue on these projects during my postdoc. Wake up. Cool, great. So as we all know, garnet is kind of the holy mineral of metamorphism. There's really, really a lot of things you can do with garnet and not a lot you can do without garnet, although perhaps some metamorphic petrologists might disagree with me. But of course, we know that garnet is really kind of one of those critical minerals that has been used for decades and decades now to study metamorphic processes, tectonic processes, and all these sorts of things. And as a lot of people know, garnet has a huge stability field. So this is just a PT diagram, but roughly with the facies. But garnet can be found in certain rock compositions, basically anywhere within this sort of pink area here. So of course, in metapelites, where we have more manganese and things like that, we can grow abundant garnet. But garnet is also very present at high pressure conditions. And because of that, people have really started using it to unravel geodynamic and tectonic problems. So, of course, where do we find garnet in the crust? It's a bit of a question, and the answer is in a lot of places. So, as we know, in the lower crust, there's often garnet stable. In sort of collisional settings or mountain belt settings, garnet is also stable. In subducting slabs, we have garnet present, and of course, in the mantle, a huge amount of the mantle has garnet present as well. So because of this, it's actually really useful to unravel quite a lot of geodynamic scenarios, and this isn't all of them. So I think that we all know the usefulness of garnet, and it really doesn't need that much introduction, but I'm going to do it anyway because why not? So some of the first information we can always get is, of course, just down the microscope. We can have textural information. What are the inclusion assemblages in garnet? What do they tell us about the prograde history of the rock? They can also form inclusion trails, like in this beautiful picture, which tell us something about the deformation history of the rock. And also we can find out about the relationship between the matrix and the garnets. So in a way, they can kind of often encapsulate everything from prograde, peak, to retrograde metamorphism. Again, the major element zoning and composition is also critical. It's been studied for a long time, and it's very routine now to look at this. So these are just some EPMA maps of garnets where we can see the classic manganese Rayleigh fractionation zoning, but we can also see changes in the calcium, the magnesium, which might reflect changes in PT, they might reflect changes in fluid composition, bulk rock composition, all of these things. And garnet is a beautiful recorder of all of these in just its major elements, just its chemical makeup. Then, of course, we can use garnet for thermobarometry and phase equilibrium modeling. It's incredibly useful for working out and quantifying these PT conditions that the garnet formed at. And this is just a diagram from Baxter et al. Showing a PT diagram with pressure, temperature, and it's contoured for the ion composition, almandine, of our garnets. So if we have our measured major element composition of our garnet and we make a forward model such as this, we can really start to quantify and connect the exact PT conditions that our garnet grew under. And this is incredibly powerful tool. Just to add to all of this, garnet also takes in trace elements, and this is also a really interesting field. So here I have laser ablation maps. This is one of lutetium, one of the heavy earth rare elements. Here is just the rare earth elements in just a spider diagram, and you can see that garnet from its core to its rim has quite a varied trace element composition or rare earth element composition, which might reflect its growth. But also, it takes in other trace elements such as things like chromium, titanium, and these sorts of other interesting elements. And altogether, this can tell us a lot about the growth conditions of the garnet, which accessory phases or other silicate phases were stable and breaking down during the growth of the garnet. And laser ablation mapping of garnet has become, again, another really powerful tool that we can use. So to add to all of that, there's lots of other things, and I have not included them all. But of course, diffusion studies and spinometry from looking at the diffusion of elements in garnet is a really powerful tool for timescales, understanding the timescales of cooling and metamorphism. Isotopic systems such as oxygen, lithium stable isotope systems are becoming a really interesting way to investigate fluids. This is a really nice figure from Beauvais et al. With in-situ oxygen isotope analyses. And garnet can also incorporate water, which is shown in this map down here, which is a garnet mapped for titanium and also water content. So it can take in small amounts of water, which is also really interesting. And there's so many more. But the thing I really want to focus on today, of course, is geochronology. So how can we date garnet? The answer is via a lot of methods, but I'll focus on some of the more common ones. The first one is uranium-lead dating. This has been used historically quite extensively for dating mineral deposits such as skarn garnets, but now is becoming a really wonderful technique for dating just normal metamorphic, pilitic garnets using laser ablation, ICP-MS. And here's just an example of a nice common lead isochron of a garnet on a Terra-Wasserberg diagram, where the lower intercept allows us to constrain the timing of garnet growth. So that's really exciting. I'm super excited to see what comes out of that in the future. Samarium neodymium is quite a traditional method. It's been used for a long time, and this is done by, by column chemistry, so solution extraction of these isotopes and then measurement. And here's an example from Pollington and Baxter, where they've managed to take out different zones of their garnet by drilling and milling. And then they've processed those garnets for their samarium neodymium isotope measurements, and they've sort of made a nice constraint on the timing of garnet growth, or more so actually the duration of garnet growth, which is really powerful. But also you can use that, of course, just to date your garnets as you wish. It doesn't have to be so fancy. And finally, lutetium hafnium, which is my favorite method, which has been used for the past few decades, but in some ways is often more successful than the previous two methods, specifically because garnet fractionates lutetium so heavily over hafnium. during garnet growth, and this is just a nice laser ablation garnet map. Garnet really heavily fractionates the heavy rare earth elements like lutetium into its core. And hafnium definitely less so. So you have a really high parent-daughter isotope ratio, and this is really powerful and helpful for dating methods. So how do we do this? So if you don't know how an isochron works, you're about to learn. If you do know how an isochron works, sorry. But basically, as I said, the garnet takes in heavily fractionates lutetium during its growth. In this case, we're interested in lutetium-176. This is the radiogenic isotope of lutetium. It makes up about 2.5, 2.6% of all lutetium. And to a lesser degree, the garnet takes in some hafnium, but it does take in some. This is why we have to use isochrons. And that hafnium is comprised of various isotopes, but the two we're interested in is hafnium-176, which is radiogenic, and this comes from the decay of lutetium-176, and 177 hafnium, which we use as our common non-radiogenic hafnium. So what that looks like if we look at an isochron diagram, where on the x-axis we have our radiogenic parent, 176 lutetium, over 177 hafnium, which is stable. And on the y-axis, we have the radiogenic daughter, 176 hafnium, again over our stable hafnium. You can see that the garnets have really quite high lutetium-hafnium ratios. So they plot over here. And this is because they're fractionating that lutetium. So this lutetium-hafnium ratio is high. And the hafnium-hafnium ratio will reflect something like what the bulk rock or the bulk matrix, whatever you like, whatever the rest of the rock is made of, which is shown here. So they're in equilibrium. And most of the time you will hope that your garnets have a lutetium-hafnium ratio of at least more than 1. If it's less than 1, you're probably in trouble. So that's what you hope for. Then with time, we have the ingrowth of 176 hafnium from the decay of 176 lutetium. So your garnet points with time will increase their ratio of 176 hafnium to 177 hafnium. Your whole rock will also do the same, just to a lesser degree because it has less lutetium. So this is basically proportional, the shift is basically proportional to the amount of time that hafnium has been allowed to ingrow in your garnet. And this is all, I should say, assuming a closed system. So you haven't had any diffusive loss of any of your elements to the outside matrix. Your garnets have remained closed and kept their composition. And then, of course, you can calculate a line through these points, and the slope is directly proportional to the age. So it sounds pretty straightforward in theory. But a really important thing, of course, is that you need a spread in lutetium-hafnium ratios for this to work, because this regression has to go through as many points as it can, as far away in lutetium-hafnium space as possible. If they're all together clustered, e.g. if we only measured our garnets here, there would be lots of possible solutions for this regression, and you would end up with a really large age uncertainty. So this spread is really important, and that's why traditionally we measure something with a low lutetium-hafnium ratio to help constrain this slope. But as you may have noticed, something a little bit pesky about this situation is that lutetium-176 and hafnium-176 have the same mass as hafnium is formed by beta decay. To add to it, there's a nasty little guy down here, which is 176 ytterbium. Ytterbium is next to lutetium in the periodic table and is also incorporated into things like garnet. And as you know, in mass spectrometry, we like to measure things by their mass. So if we were to attempt to measure mass on 176, essentially, we would have an interference of all of these elements, and that makes dating impossible. So to overcome this, a lot of people have developed a method called column chemistry. So the column chemistry allows you to chemically separate out your lutetium, your hafnium, and your ytterbium in the lab. And that's what this picture is on the top left here. This is a clean lab from the Polish Academy of Sciences in Krakow, where I spent a lot of time once, doing this column chemistry to extract the different elements from my garnet. And usually what you do is you take your whole garnets, you crush them, you try to remove some inclusions, and then you analyze bulk aliquots. And then this is all measured in each sort of aliquot is measured independently using multi-collector ICP-MS, but it can also be done by TIMS. So this is from the same lab. So this is a great technique. It's highly precise, really, really precise. You get amazing. I think some of the ages are coming down to like 0.5, 0.2% uncertainties on the individual analyses, so that's just amazing. And the removal of inclusions is very possible. You can crush your garnets carefully. You can try to take out things like your zircon, your apatite, your rutiles. And there's also methods of digestion. So when you digest your garnet, you can try to leave the zircon behind. This is all possible, although I will admit not the easiest task. Really cool, a really cool thing that's been developed lately. So there's been microdrilling around, which is essentially you use like a dentist drill to drill out your bits of your garnet. But now there's a new development of laser ablation drilling, which is even more precise. So here's a nice image from Toile et al., where she has gone with a laser mill and drilled it out. You can see she's drilled out this zone in her garnet, this zone in her garnet, and also her garnet core. And then she's taken that material and done her column chemistry, et cetera, on them. So this allows really cool control on that exact little zone of garnet. However, it's a bit difficult because for this method, you need a lot of material. So I think she had to combine a lot of these zones in order to actually have enough material to go through column chemistry. But still an awesome technique and really, really important if you're interested in highly precise dating of your garnets. The downsides is that it's really time consuming. You need this large quantity of material needed, as I said. So that means that your spatial resolution is quite finite. And there's still some uncertainty. You know, you crush up your garnet, you're like, have I included some zircon? Which zones in my garnet are included? Is this core dominated? Is this rim dominated? How does this work? You kind of lose a lot of this information. So that's where I come to LA-ICP-MS, which is all made possible by this little machine here on the right, which is what we call a triple quad, or QQQ, but triple quad I like. It's more, I think it's cuter, more affectionate. And that is coupled here to a laser ablation cell where we can physically ablate our garnets. So the laser ablation cell is really cool because it doesn't do that. I wish it did that. I don't know if you've ever been in the lab and someone's really annoying you and you wish you could just like shoot a laser at them. Yeah. Unfortunately, the laser isn't that big. It can only fire at the little garnets. But the key thing that kind of allows, so this is what it looks like, I should say, sorry. Here's a garnet in reflected light and you can see each of these little black pits I've circled is an ablation pit where we've taken one analysis with the laser. But the key thing that lets this all work is in our mass spectrometer, in our triple quadrupole over here, we have a reaction gas. And this is sort of the critical point. So to go into that further in a bit more detail, so here on the left, we have our little garnet that's been ablated. The material travels to the mass spectrometer where we have two quadrupoles, quadrupole 1 and quadrupole 2. Between them is another quadrupole, which actually is a collision cell or a reaction cell. And in here, we put a reaction gas. In the case of lutetium hafnium, it's ammonia. So the first quadrupole acts as a mass filter. So you take only your isotopes of interest. In this case, we've got lutetium, ytterbium, hafnium 176 are allowed to pass into the collision cell where they react. And the key thing here is that the hafnium 176 reacts with quite a large compound, this complex compound here, to make a big anion with the hafnium with the mass of 258. Sorry. This is then allowed to pass through the second quadrupole and eventually be passed to the detector. The thing that makes this work is that lutetium and ytterbium react with one more hydrogen than the hafnium. So their mass is no longer the same as the hafnium, it's one higher or actually several lower. So this is perfect. We've managed to chemically separate our hafnium on the fly within the mass spectrometer during analysis. And I should say there's a little bit of, a little bit of interference. We have about 0.003% of our lutetium 176 overlaps on this mass and much less of the ytterbium. But this is a really small overlap and we're able to correct for it during data processing. And we can use this technique to date garnet, obviously, or you can use it to take apatite, xenotime, and calcite as well. And if you're interested, we have the methods paper, it's in chemical geology. And the cool thing I want to point out is for garnets, we're doing a lot of isochron geochronology, but for some garnets and some other minerals here, we can actually do single spot ages. Apatite, for instance, takes no hafnium in, so you can essentially do like you would in uranium lead, single spot ages. So it's quite powerful, not just for garnet, something to keep in mind. So looking a little bit more on the analysis and the data, on the left here, I have some example laser ablation signals. So we have time on the x-axis and just intensity on the y-axis. And the key thing I want you to look at down here in B is that these are the lutetium-hafnium ratios downhole. So as we're drilling down into the material, and there's no downhole fractionation, the ratio stays relatively constant, and that's really helpful for laser ablation geochronology. So a little bit about the logistics. For garnet, the spot size is usually 80 to 120 microns, but it's quite flexible. Really, really nice things that you can simultaneously analyze lutetium and hafnium isotopes as well as trace elements at the same time. And this is super useful. So you can collect some rare earths if you're interested. You can collect things like the zirconium, the titanium, the phosphorus. And by doing this, you are able to monitor for inclusions. You can really check which part of the garnet you're ablating if you're going through different zones or something. And this turned out to be way more useful than I previously had thought it would be. So that's really nice. Right now, the primary reference material is the NIST 610 glass. So the eternal pain of method development with the laser ablation is that it's really hard to find homogeneous and matrix matched isotope standards. And of course, the same is true for lutetium hafnium, especially in garnet. So we currently don't have a garnet lutetium hafnium isotope ratio standard. If you can think of any garnets or if you know of something, please let me know. But what we have to do right now is we use the glass. And we have like a secondary standard, which we call our age standard. And this is a garnet called the Hobsbawm garnet. And basically we're able to correct for any sort of matrix problems by using an age offset correction. So a bit more about the Hobsbawm garnets. They look like this. They're from a rare earth pegmatite, which is actually found in Gothenburg in Sweden. And I collected these and thought, okay, it's a rare earth pegmatite, like the lutetium hafnium is going to be awesome. And of course it is. So here's the results. This is over about 5 or 6 analytical sessions, and you can see that the Hobsbawm garnet produces lutetium hafnium ratios of up to 10,000, which is crazy amazing. And because of that, we get a really highly precise LA-ICP-MS age of 1,052 million years. However, the pegmatite itself is not that age. It's probably around, let's think, 1,029 million years, although we have some preliminary traditional column chemistry lutetium hafnium data from the garnets themselves, which looks more like they're maybe 10,020 million years old. 1,020 million years old. So this means that our age offset is around 3%. And that's basically the offset which is calculated from the difference in the laser ablation age and the difference with the column chemistry age. And that's how, when we then applied that offset to our measured data from the session to try and sort of correct for anything. The reason this happens is kind of a bit unknown, but we suspect there's a matrix problem. So between ablating the glass and obtaining the lutetium hafnium ratio from the glass and ablating our garnets, it's a very different matrix. So we assume that's where this offset's coming from. But with more column chemistry dates from our Hobsbawm garnets, we're going to try and resolve that soon. So that was enough methodology for one day, I think. So now we can go to some examples with a focus on high pressure rocks. And why high pressure rocks? Because I did my PhD on high pressure rocks. And also I just think they're really neat and very, very interesting rocks to study. So I'm going to show you 2 examples now. And with some kind of like takeaways, I really want you to take from these examples is what I think are some of the benefits and cool applications of the in-situ lutetium hafnium method. And that is targeted analyses. So the really, really high spatial resolution to be able to target garnets, look for the really high lutetium parts of the garnets, take conclusions or not take conclusions, this kind of really targeted analysis, which I think is really cool. And then other things I think are really cool is the idea of campaign-style dating. So the acquisition of age data from a huge metamorphic terrane. And also, of course, a really obvious cool application of this method is to find polymetamorphic garnets. So polymetamorphic garnets are simply garnets that have 2 metamorphic histories recorded in them from different tectonic events. And usually you see this as a core-rim ratio, where the core is older from one event and the rim is younger from a later event. So example 1 is from a place called Port Macquarie in Eastern Australia, where I did my early PhD. So if you're not familiar with Australia, here's the east coast of Australia. which was all basically created by this huge subduction complex in the Cambrian to Ordovician. So the subduction that's recorded at Port Macquarie is around 490 to 450 million years old. So it's an outcrop all the way out here on the beach in New South Wales, north of Sydney. And it's a really, really complex, very beautiful subduction melange. So you have high-pressure eclogites, high-pressure blue schists, sediments all mixed in. And this is the sample I want to show you. It's a really beautiful lawsonite eclogite. And you can see these gorgeous euhedral garnets. In the matrix is phengite, omphacite, and lawsonite. So when you look at that, you think, oh yeah, that's great. Look at those garnets. We can date that. And of course, that's what I tried to do in my PhD. However, it wasn't so easy. So here is a laser ablation map of one of the garnets coded for lutetium. And you can see that the garnet cores actually are very high in lutetium. They have about 12 ppm. But the rest of the garnet has somewhere between 1 and maybe 8 or 9, 10 ppm. So they're fairly enriched in the core, but fairly depleted in the rim, which is classic. The problem is that they contain a lot of zircon inclusions. And the more garnets I look at, the more I'm starting to find out this is a very, very common phenomena. Tiny zircons between 10 to 15 microns big, very, very hard to get out when you're crushing your garnet for conventional lutetium hafnium geochronology. And if we look at the column chemistry or the solution age here, we see the result of that. So we have a lutetium hafnium age of 487 plus or minus 11 million years. This is quite a large uncertainty for this method. But that's because the lutetium hafnium ratios in the garnet are so low, only about 0.16. Down here we have the whole rock, and along here we have some lawsonite fractions. So it's pretty clear that this garnet analysis is not pure garnet. If we have a garnet with 12 ppm, even with low in the outer rim, it should still have a higher lutetium ratio than that. So it looks like the garnet is very much dominated by zircon, despite the fact that we tried really hard to remove these zircon inclusions. So that's all fine. I mean, that's the solution age we got, and we had to publish it. But then later, following up with this lutetium hafnium method, I decided to analyze the same garnets. And here's the in-situ triple quad data. So the ages are around the same. We have about 481 plus or minus 23 million years. As a rule of thumb, the in-situ method has a much higher uncertainty always on the ages because each individual ellipse has a much larger uncertainty compared to the tiny, tiny points we produce via the multi-collector. But you can immediately see that we've reached lutetium hafnium ratios of up to 60. And there are also some sitting around here that are around 20, and there's a lot that is certainly higher than 0.16. So by doing this, we've managed to actually hit pure garnet without significant zircon. And in this way, I'd actually be more certain that that's the age of the garnet, even though the precision is not as good. The uncertainty is larger. To look into that in more detail, here's that same isochron, but now with the power of the in-situ method, we can color code for any of the elements we collected during our analytical session. So here I've color coded for zirconium, so the orange colors have higher zirconium content, and the more purpley colors are closer to pure garnet. And if we zoom in down at the bottom of the isochron here, but even here, you can see that there are some analyses that have quite high zirconium. So they're not pure zircon, but they definitely have some amount of zircon mixing. And you can see it along here. So that's kind of nice because if you did not want your zircon, any zircon in your analyses, you could kick those out. You can be like, nah, we don't want them. That's mostly looking at the lutetium hafnium ratio and the zircon. But in this case, the key really is that the zircon inclusions are cogenetic with the garnet. They're actually the same age, which means we can use them on our isochron. And I love that because what we can actually do is we can be like, no, our zircons are cogenetic, they grow at the same time, so we want to use them down here to anchor our isochron. And just for comparison, if we look, this box here is roughly the size of the box for the solution ages with our very low garnet lutetium hafnium ratio. So we were really only looking at this lower end, but if we expand it and we're able to find analyses in the very core of the garnet that don't have many zircons, we're really able to improve. So what does that look like in the laser ablation signal, you might be wondering? So this is a laser ablation signal from one of those garnets. And this is in the Ladder software. I don't know if anyone's used the Ladder software. I can highly recommend it. It's really great for processing of laser ablation data of all types. So along the bottom, we have sample time. So over here is our background measurement. And then here's when we start ablating the garnet. And this is just intensity. And I've highlighted the zirconium, hafnium, and lutetium signals. And you can see right here where we hit a zircon, it's in this dark purple color. Of course, our hafnium goes up. Zircons on average have like 1.4 weight % hafnium or something like that, or less. But the lutetium, of course, does not change because the lutetium is dominantly in the garnet. So if we took this section, we have an analysis with a very low lutetium hafnium ratio, and if we took this section, we would have pure garnet with a high lutetium hafnium ratio. And that's the power, because we were doing exactly that. We were making one integration that's zircon dominated and one integration that's garnet dominated. And then in the end, that's kind of achieving this spread in your lutetium hafnium ratios that you need to have a good regression to get an age. So this method, you can't really analyze your whole rock per se, but you can analyze high hafnium phases, such as rutile, such as zircon, as long as they're cogenetic with your garnet, to constrain the bottom of your isochron. So you're really starting to achieve that spread in lutetium hafnium space. So example 2 is from the Western Gneiss region in Norway, which is quite a famous high pressure terrain. So here is a map on the left. Sorry, there's a lot of data on there, but what I will draw your attention to is in purple, you can see these dashed lines. These are rough isotherms. So you can see that we start at lower temperatures in the south here from under 600 degrees. And as we head to the northwest, we increase to over 800 degrees. And these temperature isotherms are accompanied by pressure isobars. Sorry, so you can see in orange dashed lines, we start down here at lower pressures, less than 1.8 GPa, but down here, they're only about 1.4. Increasing up to 2.4 and then really increasing again in the northwest direction. And then you have these yellow lenses, which are outlined, and they are actually ultra high pressure domains. They're domains where the pressure reaches about 3 GPa or higher. So basically, this entire section of continental crust was subducted to high pressure to ultra high pressure conditions. And this subduction event is called the Caledonian origin, and it was around 400 million years ago when the margin of this continent was subducted. So if we look at that in sort of like a 3D, so we have increasing pressure and temperature as we head north. And if we look at that in 3D, this is a really nice model from Hacker et al. We can see basically in the south here, which is over here, we have these lower pressures. And as you go towards the north, we reach these really ultra high pressure domains. So that's essentially a model of the subducting continent at the time it was at its highest pressure, which I think is really nice. But the Western Gneiss region kind of has a bit of a difficulty in that it's continental. So it's not like we can, look at a nice mold from here and say, oh yeah, okay, we had blue schist, we had eclogites. It's continental material, which is a lot of people here will know doesn't behave so well under high pressure conditions. So what do I mean by that? So if you go to the Western Gneiss region, it's a very complex region, of course, but to simplify, you have this relationship all the time where you essentially have a Boudin, which is what I'm sitting on there, a mafic Boudin with some sort of roughly basaltic composition, and it's wrapped by a felsic gneiss. I know in this image this doesn't look particularly felsic, but that's just Norwegian lichen. So you're going to have to trust me that this is the mafic material, and out here we have our felsic gneiss. You can see some of the white rocks here. And the felsic gneiss is mostly an igneous protolith. It's tonolitic to granitic to granodioritic gneisses that encapsulate all of these Boudins, which were probably once dikes or intrusions. And this was all formed well before the subduction event, of course. So if you hit these rocks a lot, you have to really trust me here. The Boudins look something like this. They're beautiful eclogites. Sometimes they're retrogressed, sometimes they're not, but they're beautiful garnet omphacite assemblages which record this high pressure subduction. And they're very well studied and very well dated, of course. If you go to a terrain like this, you go to the eclogites, like guilty, of course you do. So they're very well dated. Everyone knows really when they formed, the duration of subduction, and the exact conditions, as you saw from that map before. But if you go to these encapsulating felsic gneisses, you're usually pretty disappointed. They look something like this, like the least exciting metamorphic rock possible. They're gneisses, cool, but they have these really boring low pressure assemblages. I'm sorry if anyone's getting offended by this. I maybe should be nicer to the felsic gneisses, but They're plagioclase, quartz, biotite, hornblende, titanite. Nothing about that screams high pressure. I mean, they're abundantly plagioclase. As we know, plagioclase should not be stable at ecloditic conditions. This should look something like a jadeite, garnet, muscovite rock. That's what it should look like, but it almost never does. And these are studied as well, maybe a bit less. They're quite well dated, so people have an idea of when these gneissic rocks formed. The protoliths are usually, they're what we call speckle Norwegian, so about 1,000 or so million years old, 1 billion years old. But it's really unclear why they didn't react. Well, did they not react during high pressure metamorphism? Were they metastable? Or did they react to form beautiful high pressure assemblages that have now been retrogressed? We don't really know the answer. I suspect the first one is true. But sometimes you're lucky. So if you're looking in these felsic gneisses, what you actually find are lenses of metapelites. And this is a beautiful metapelite from the north of the Western Gneiss region, which is a garnet, quartz, kyanite assemblage with retrograde biotite and plagioclase. And like this, you can say, okay, cool, this went to high pressure, this reacted. And sometimes if you're really lucky and you really look, you find felsic gneisses that are still this lovely plagioclase biotite assemblage, but they have garnets. As you can see, there's a garnet here and a small one here and here. So, okay, woo, garnets, like maybe they did experience some kind of high pressure condition, but the question is when? So, of course, we wanted to attempt to answer this in some way. So we did a huge sampling across the Western Gneiss region, mostly focusing on these quartzo-feldspathic, tonolitic, granodioritic rocks, but also picking up a few metapelites. And if we return to the map, all of these little stars are a sample location, but usually there's a few samples from that location of different lithologies. And you can see we really focused on the ultra-high pressure domains to try and find metapolitic samples that definitely should have seen ultra-high pressures, as well as some from lower pressure conditions to compare. And they're pretty normal garnets in these rocks. So the lutetium in the garnet is usually between less than 1 ppm to 130 ppm, which is extreme. But most of them are between 5 to 40, which I think is quite normal for metapolitic rocks. And our real question was, these other metapolitic and quartzo-feldspathic lithologies reacting during the Caledonian orogeny, so during subduction, and are they growing these garnets during subduction? Are they related to that? So we undertook this campaign-style dating. Sorry about the overwhelmingness of this, but I just wanted to kind of show you the workflow in that what we did was we took all of our samples, we mapped our garnets using a micro XRF mapper, and we mapped for major elements, so calcium, iron, magnesium, manganese, etc., but also yttrium. And if you can't map for lutetium to see where it is in your garnets, yttrium is incredibly helpful because it behaves something like the middle rare earths. So it behaves quite similarly to the middle rare earths, which are quite similar to the heavy rare earths. So you can kind of use it as a proxy for where your lutetium will be. So we did that, and you can also map for yttrium on a probe and those kinds of things as well. So we did that, mapped all of our garnets to find places with high yttrium that we could analyze, but of course also we wanted to analyze low yttrium parts of the garnet too. And then we went crazy on the laser, as you can see from all of these isochrons. It's very overwhelming, but what I kind of want to get across is that you can do something kind of like people do in terranes where they go and they take rocks from all over the terrane and they date all the zircons, or they date all the titanites, and they try to say something about the overall patterns of metamorphism or temperature increase in the terrane. And I think this is a possible really, really cool thing in the future that people can do using this, because you're actually dating the garnets, you're directly dating the metamorphism, you're not dating an accessory phase. So I really am looking forward to people doing that, hopefully, in the future. So the results, just to summarize all those terrifying isochrons, are here where we have age on the y-axis, and then south to north increasing along here. So south at the lower pressures and north at the higher pressures. And you can see that these are each of the individual isochron ages. You can see that the majority of the garnets are around Caledonian in age. They're slightly older, actually. They're just over 400 million years. And because the age uncertainties on each isochron are quite large, we aren't really able to deduce many patterns within the Caledonian event. That's for two reasons. First of all, the Caledonian event was very short. It was probably only 20, 30 million years. So it's quite hard to resolve within that time frame using this method. But also because some of the garnets have very little lutetium. But I think in the future, perhaps, as the method continues to get better and more sensitive, we can hopefully start to resolve things on these sorts of timescales. But of course, your eye will be drawn to that there's two areas that have older inherited garnets. So the first one is a place called Fjordhoft. You can see there's a bunch of old garnets here. This is a really famous location up here in the north. You can see it here. It's actually meant to be a diamond-bearing metapelite. Pretty much all of the geochronology has said that the high pressure metamorphism there is Caledonian, but we found quite a strong imprint of these older ages. So I think we kind of need to be a bit more careful there. Go back, look at our garnets, make sure which garnets we're using to infer the conditions, because there's definitely two generations of garnet all over that island. The second place is Vapenicet, which I'll sort of zoom in here. So here's Vapenicet. It's here in the sort of mid-south. And this is a really interesting location because it's directly on the edge of one of these ultra high pressure domains. And here we found older garnet as well as younger garnet. So just to look in the field a bit here. Here's a really nice picture I showed you before of the Vapenicet eclogite. It's very famous. People know it just because it's like one of the most beautiful Christmas tree rocks ever. You can see the red garnets, the green omphacite, and this white material is actually clinozoisite or zoisite. And this has been super well studied. Like people really know it's, it was definitely formed in the Caledonian, what conditions, etc. So the outcrop's pretty average actually. So up here you can see a road. You have to kind of like scramble down this embankment that's all loose like towards the fjord. And here on the bottom left, you can see very in the sunshine, like the green, red and white rock, which is this eclogite. And surrounding it is this, of course, incredibly boring, very inconspicuous felsic gneiss. You can see it's quite foliated on the edge of the boudin of the eclogite and more massive out towards here. And if you sample this is again one of these granitic tonalitic gneisses, and it has the mineral assemblage garnet, muscovite, quartz, biotite, plagioclase. So the biotite and the plagioclase, low pressure minerals. The garnet and muscovite maybe gets you a bit excited. You think, oh, okay, maybe this has recorded some of the high pressure subduction that these rocks directly next door, within a few centimeters, have recorded perfectly. So if you look at the garnets, these are some of these micro XRF maps. They're quite interesting. You can see that there's this rim here, which is an inclusion rim, and it's surrounded by a nice annulus of enriched calcium. And the yttrium is quite interesting. Usually you see an enriched yttrium in the core. Here you don't, but you see enriched yttrium on the rim. So they're quite interesting garnets. And of course, you might look at those maps and be like, ooh, they're polymetamorphic. And you would be right. So if you look in the core here, which is sort of the inside of this white dashed line, we have an age of about 913 plus or minus 63 million years. There's a large uncertainty as there aren't many analyses with high lutetium. This was quite hard actually to date, possibly because of the really low yttrium, so it's also low in rare earth elements, but we're able to get this age with a large uncertainty. And then the rims are really nicely constrained at 405 plus or minus 25 million years. So this Caledonian subduction event. And I just kind of want to point out, even though like the lutetium contents are a bit average, and also we have large uncertainties on the ages, I think it's with ages that are this far apart, you have no problem in discerning polymetamorphism. A lot closer, within 100 million years, you might start to see problems. But outside of 100 million years, if you have enough lutetium, you really have a good shot at being able to discern the two age populations in your polymetamorphic garnet. So this is cool. So an outcome of this is that probably more than was previously identified, there's this inherited speckle Norwegian metamorphism, so this 1000 MA metamorphism, that seems to be throughout the basement of the Western Gneiss region. And I would love to do more garnet dating to see how pervasive this metamorphic event is throughout. But the other cool thing is that these garnet cores here, they've survived a whole metamorphic event, a subduction event that went to, in this area, up to 2.8 GPa and, over 700 degrees. So these garnets have managed to survive that entire new event, and I think that's really cool, and keep their age. I think that's really interesting. So a question you might have now is like, Renée, that's all well and good, but will my garnets work? So I'd like to have a word on the uncertainties involved. So here are two plots with all the dates from the Western Gneiss complex, or Western Gneiss region rather, sorry. And on the y-axis, we have the uncertainty on the isochron age in percent. In the top plot here, it's just highest lutetium content in micrograms per gram or ppm, whatever you prefer. And down here, I have highest lutetium-hafnium ratio. That's kind of less useful because you never know the lutetium-hafnium ratio really of your garnets, because that's dictated by knowing the hafnium, knowing the lutetium, knowing the age. But the highest lutetium is, we can measure that on the laser or whatever, and you can basically see the relationship looks something like this. So if you want something with an age uncertainty of less than 10%, you definitely need at least 10 ppm lutetium maximum. So what I mean by that is that maybe you need an area of your garnet that is enriched in lutetium of at least 10 ppm, but you can have other parts of your garnet that are way lower than 10. That's just kind of what you need on the top part of your isochron to pin it. So, as I said, will my garnets work? Depends on your research question, for sure. You have to be willing, you have to have garnets with at least 10 ppm somewhere in them, maximum. Your question has to be okay with having a 4 to 5% age uncertainty. If that helps you answer your question, that's fine. And I would say generally, or no, not as a rule, but in general, you want domains of your garnet that are inclusion-free, or as much inclusion-free as you can manage, of around 100 microns. It's quite big, and as I showed you in the laser data, you can filter out your inclusions, but you really need to guarantee that you have some analyses that are fully garnet, and you need to make sure that you're not dating inclusions such as apatite, rutile, and zircon, or xenotime, even worse. So just as a sort of summary, I'll say the negatives is for sure. It's not as precise as traditional methods. That's definitely true. But I think some of the positives are that you can analyze a lot of samples in a short time. You have this amazing spatial resolution and control on targeting different textures, zones, compositions. You can simultaneously collect your trace element data, and you have this real power to choose to include or exclude inclusions. You never know, oh, was there an inclusion in my aliquot? You know, because you can see the inclusion and you can say, I don't want that in my analysis, or I do. And I think that's incredibly powerful. So some applications that I covered or I think are cool in the future are, of course, identifying polymetamorphism or inherited garnet. That's obviously a powerful one. I think campaign-style dating, well, perhaps I didn't sell you the best example. I would just love to see people using this across terranes, across places like the Himalaya, who have just huge mountain belts, to really look for age patterns in the garnets. I think another cool use is just fast reconnaissance, like just checking how old is this rock? Like, is it part of this terrane? Is it part of this terrane? Is it in this unit or not? Just quickly checking could be great. Also, something I've used it for a lot is a situation like this picture here on the right, where I have these garnet porphyroblasts and fine-grained garnets, and I want to make a PT model, and I want to, do this in thermocalc or perplex, and I have my bulk rock composition, and I'm like, which parts of my garnet are in this reactive assemblage? And many times I found that the porphyroblast is actually inherited. It's from like 500 million years prior to the metamorphic event I'm trying to model. And that's in many ways, quite useful to be able to say, okay, that garnet is being excluded from any part of my PT modeling. I think a cool future application could also be the rock and garnet reactivity during metamorphism, like when a rock's reacting, kind of like I tried to do in the Western Ice Complex. And maybe in the future, something like detrital garnet studies. And I'm sure there's lots of others. And if you have any ideas, I would absolutely love to hear about them. So that is me done. Thank you very much. If you want to set up this method, I still have some of the Hogsbow age garnet age standard available, and I'm very happy to share it. And yes, also thank you to these people who helped make this all possible. Great.
Thank you so much, Renée. It was amazing talk, very interesting. Also with the part for the methods and also with the applications. Everyone who has a question can send it in the chat, and we already have some from our group. So we started with Bruno, and then we followed.
Mm-hmm.
Absolutely amazing. Just to start like this.
Thanks.
Yeah, pretty good. I have a little, I'm doing Garnet myself as well. So I have a few questions in terms of methods that I've been thinking. So the first thing is hafnium contamination in the carrier tubes, for example. So if you use the same tubes for zircon lutetium hafnium and then for garnet lutetium hafnium, does it make a lot of difference, or do you think that the carrier gas actually makes a good job in cleaning the tubes?
That's a really good question. We analyze a lot of zircon in our lab, and we keep pretty good track of when there's been recently a zircon or even a rutile actually, say uranium lead session, and then following that, what do our standards look like? But we've never seen any effect. In fact, the reproducibility across the sessions, because we run one basically every month for a week, is pretty good. So I'm going to assume by that the carrier gas is effectively keeping the tubes clean. But maybe if you needed to go more precise, so maybe in the future you might see it starting to become an issue, but it's a good point.
Yeah, maybe it should be better to use just individual tubes for different methods, so we can avoid that maybe.
Absolutely, if you have a lab tech who's willing to change them, of course.
Yeah, that's true. Second question quickly. The problem with the Garnet lutetium hafnium is the matrix matching standard, right? Do you think there should be, I know it's very speculative at this point, but do you think it should be like a matrix effect controlled by garnet chemistry? Let's say more spessartine garnet should behave different as like grossular garnets or something?
It's definitely possible. I think you might see, there's actually quite a few concerning things there. So the difference between glass and garnet is obviously very large because we see it. That's why we have our age offset. Between different garnet compositions, I wouldn't be too worried. The thing I would start to be worried about is if your garnet is no longer cubic, if it's tetragonal. We know that can happen at low temperatures. Bernardo Cesare has been showing that. That I think is possibly going to have an effect as well. But perhaps once we have a matrix match standard, that can be something we investigate. I think that would be really interesting to look at. For sure. Cool. Thank you.
Okay. I'll let other people talk, otherwise I'll just stay here forever.
I'll stop my screen. Yeah.
Renée, it was really interesting. I have a question. I don't know if it's right for the tectonic setting, but for the older ages that you found in Norway, one was for the metamorphics, right?
Mm-hmm. Yeah.
And I was wondering also, because you have shown that garnet can be stable for a huge range, would it be possible that actually these are detrital garnet cores and not metamorphic?
That's a great question. We considered that quite strongly because that was always the argument. People had found in the metapelite old monazites, and they said, "Oh, they must be detrital. Like this is a fresh pelite, it's in the ocean floor perhaps, and it gets subducted." But I mostly discluded it for a few reasons. One, the abundance. So the old garnet made up I think it was around 20% of the rock. That's like a lot of detrital garnet. Also, they were huge. They were about 1,500 microns to 2,000 microns across, which is possible, right? If you have a really, really local source, there are some beaches in the world where you have a super, super local source and you have like a metamorphic rock that is eroding. But it's incredibly rare to actually find that now in the modern record, and to find garnets that big and well preserved in that volume. So unless there's places I don't know about, there probably are some nice, really special cases, but having it preserved, I think, would be incredibly, incredibly difficult. Also, when we looked at the garnet the garnet chemistry is all the same, the ages are all the same, so it would have to come from one source. And even though we only see part of this sedimentary sequence, it's quite thick. So you'd have to have the sedimentary sequence coming from one source of one metamorphic rock and preserving your large garnets. I would just say it's unlikely that they're sedimentary, but not impossible, is what I would say.
Yeah, maybe doing some oxygen isotopes, trying to separate with something more precise.
It's possible. Yeah, absolutely.
Thank you. I will ask another question before we put the comments because I'm very curious. Did you hit by any chance also rutile inclusions when you were analyzing, because they can also host some hafnium, right? Absolutely. I was wondering if we can also take advantage because I always thought the zircon would be a problem, and you showed it's great sometimes to have them together. What about the rutile?
That's a good question. So the rutile is actually almost better to hit because you can be more sure that it's cogenetic in a way, like unless you date your zircons and they're the same age. But the rutile is really cool because it's like, in this case, it's diagnostic of high pressure. So you have your garnet and your rutile, you're like, I think these are both in my high pressure assemblage. And actually, in that big screen with all the isochrons, most of those isochrons were pinned by rutile from the matrix, actually, because I dated the rutile and I was like, it's the same age. So then I was hitting the rutile in the matrix and using it to really pin the bottom of my isochron. And it increases the precision on the age calculation a little bit. So rutile, again, not as strong as an effective as zircon, but can definitely be really useful, or can be dangerous, depends how you want to see it.
Thank you.
Yes. Yeah, no worries.
I also have a question. First, thanks for the lecture. It was really, really fun and really interesting. So wide opened eyes for things. I was just curious about, and you just mentioned this as well, talking about this correlation between using garnet and zircon, the coexist somehow. And I was thinking about how to attest the coexistence without actually dating the zircons, maybe using some like rare elements patterns, if you think about anything like that.
Yeah, you could. It's a really good point if you can't date them. I mean, you can try to use textures, but inclusion textures are hard because you're like, okay, it's included, but was it there before or after? Of course, you could use the rare earth elements, but that also is maybe kind of only relative, because say you have a zircon with enriched rare earth elements, you'd say, okay, either it grew before my garnet or after my garnet, so I'm going to exclude it. But also, it's not like a unique solution, if you know what I mean. You can, yeah, so you can also have it forming because some of your garnet was dissolved, but maybe it's all at the same time. But I will tell you the secret. This is the secret, and people don't like this, but oh well, is that the uncertainties on the hafnium-hafnium ratios are huge. So if your zircon or rutile is actually 1 billion years older, it doesn't matter. It's within uncertainty of the error ellipse. So when I tell people this, and I'm like, yeah, I pinned it, I'm pretty sure the zircons coexist. They grew coeval, they grew at the same time. People are like, what? But you have to know. I'm like, actually, with this method right now, with the size of our individual uncertainties, you don't. So maybe it doesn't actually matter that much. The right thing to do would be make sure they're coeval. Yeah.
Thank you.
So do you think we can get better precisions with NEOMA using the multi-collector?
I really hope
Yeah,
so.
me too.
I'm looking forward to finding out. That would be great. I think that could help resolve some of these garnets that I'm so sure they're different in age. Like, you have a core rim difference, but it's like, 20%, 10%, and then you're like, oh, you just can't quite get the precision. And I think that is going to be really exciting avenue forward. I hope so.
Yeah, I'm very, very looking forward. We are getting ours in maybe, I think, March or May next year. So I'm like, yes.
So yeah, I mean, I hope it's high on the list of things to develop. I know the NEOMA has a lot of capabilities, but
yeah, but the Garnet lutetium hafnium in situ rubidium strontium, which is a bit more advanced already, are the top main priorities.
I'm glad to hear. How exciting! Good.
We have some comments here, Renée. Thank you a lot for your talk. It's very, very good.
Thank you.
Some people, thanks, great talk. Thank you for sharing. And we have a comment here from Bros. It's more for our group. How can I join the discussion group for consultations? Thank you. I am a geologist, geochemistry, and petrologist from Uganda. Thank you. So, Ambrose, you can send us an email, and we or in our social medias we can discussion, and you can consultations and anything.
Yes, sure. Just send us an email from the Petrochronics site, or send us some message on Twitter or Instagram. It will be great. Thank you, Ambrose. And Renée, I have another question. I promise it's the last one, because for the signal, for when you have the inclusions and the garnet together, would you have like some cutoff that it would be the minimum that we can trust for using like both signals?
Yeah, that's difficult because it probably depends on the sample and the inclusion type. In ladder, I didn't have it up, but you can add a channel where you look at the ratio, the lutetium-hafnium ratio. And if you're pretty suspect of your inclusions, if you're like, I think they're a really different age or they're from something different, you can just look at the lutetium-hafnium ratio. And if it's significantly changing where you have high zirconium or high. Another one is xenotime and apatite can also have an effect. So if you see high phosphorus or whatever, you can just crop around it by seeing how much the ratio changes. If you really need to exclude them. And that's kind of the way I usually go about it. But I think it depends on what you have. But yeah.
Yeah, thank you. So I would like to thank you, Renée, again for this amazing talk and for sharing with us all of this. And I would also like to thank everyone that followed us and enjoyed our talks as well. And also to our group that is in the backstage organizing everything. And we will have now a break and we see each other again in February. We wish you all the best for the end of the year and beginning of next year. And that's it. Thank you so much.
Thank you.
Thank you.
Thanks, everyone. Happy holidays.
Thank you.
Happy holidays.
Happy
Happy
holidays.
holidays.
Bye-bye. Bye-bye.